Welcome back. In this video, we'll create a stunning spiral animation in Java Swing. 3 colorful planets will glide smoothly along a motion path, powered by simple math equations. Let's dive in and see how it all works. First, create a new class called Spiral Motion Demo. At the very top, we import the libraries we need. AWT gives us access to graphics, colors, and basic drawing tools. Event is for handling events like timers or user actions. Geom provides geometry classes such as points, lines, and ellipses, which we'll use to draw the spiral and planets. And finally, Swing brings in the Swing framework itself, letting us create windows, panels, and manage the user interface. Our class extends JFrame, which means it becomes a window where we can draw and display our spiral animation. Here we create Spiral Panel, a custom JPanel that does all the drawing, and it also implements Action Listener to handle timer updates. Now let's look at the constructor of our class, Spiral Motion Demo. The very first line calls super with a string title, in this case, Motion Path in Java Swing, Spiral. This sets the title text that appears at the top of our window. Next, we use setDefaultClose operation. This tells Java that when the user clicks the close button, the application should actually exit. We then call setResizable false. After that, we use setContentPane. This is the key step. We replace the default blank content of the frame with our custom Spiral Panel class. Then we call pack method. What this does is resize the frame automatically to fit the preferred size of the content pane. Finally, we use setLocation relative to null. This is a simple trick to center the window on the screen when it opens, rather than sticking it in a corner. So in summary, this constructor sets the window's title, defines how it closes, locks its size, installs our custom drawing panel, sizes the window appropriately, and centers it neatly on the screen. With just a few lines, we now have a properly configured application window ready for our spiral animation. Our program starts here in the main method. The first line sets a system property that improves scaling on high DPI screens, so our animation looks sharp. Then we use Swing Utilities invoke later, which makes sure the user interface is created on the proper thread for Swing. Inside that call, we create a new Spiral Motion Demo object and make it visible. With just these few lines, the application window is launched and ready to display our spiral animation. Here we set up a few key variables. The timer drives our animation, firing updates many times per second. The value A is the starting radius, telling us where the spiral begins from the center. B controls how tightly the spiral expands as the angle grows. And theta max defines the maximum angle, in this case tan times pi, which gives us several smooth loops outward. Next, we define the state for our 3 planets. T1, T2, and T3 are their starting angles along the spiral path, spaced apart so they don't overlap. Then we set DT1, DT2, and DT3, these are the step sizes, or speeds, that each planet moves forward by on every timer tick. By giving each one a slightly different speed, the planets drift apart and create a more dynamic, natural-looking motion. Now we set up the drawing settings. The values W and H define the width and height of our panel. For visuals, we pick a dark background color, then a soft gray for the spiral line. Each planet has its own distinct shade: coral for the first, teal for the second, and purple for the third. Finally, we define spiral stroke, a line style that's 2 pixels wide with rounded ends and joins, which makes the spiral path look smooth and clean. In the spiral panel constructor, we first set the preferred size using the width and height we defined earlier, and then apply the background color. We make the panel focusable so it can react to input if needed, and enable double buffering to reduce flicker during animation. After that, we create a swing timer with a delay of 16 milliseconds, which gives us roughly 60 frames per second, and start it right away to drive the motion updates. Here we add a key listener to the panel so we can control the animation with the keyboard. We override key pressed and check if the pressed key is the space bar. If it is, we toggle the timer. If the timer is currently running, we stop it and the animation freezes. If it's stopped, we start it again and the planets continue moving. This gives us a simple pause and resume feature during the spiral animation. We also add another key listener to handle the R key. Inside key pressed, we check if the user pressed R, and if so, we reset the planet angles. T1 goes back to 0 and T2 resets to 3/4 of pi. This snaps the planets back to their original starting positions on the spiral, giving us a quick way to restart the animation without closing the program. This method, called spiral point, calculates the position of a point along the spiral based on the center and the current angle, theta. First, it works out the radius using the formula r equals a plus b times theta. The value a gives a starting offset, while b controls how tightly the spiral expands. As theta grows, the radius increases, making the point move outward. Next, the x-coordinate is found by adding r times cosine of theta to the center x, and the y-coordinate is found by adding r times sine of theta to the center y. Cosine handles the horizontal direction, sine handles the vertical. Together, they convert the spiral's polar coordinates into standard x and y positions. Finally, the method returns a new point 2D with these values. Each call to spiral point gives the exact location where a planet or dot should be drawn, letting the animation follow a smooth outward spiral path. In this method called Draw Planet, We take in 5 parameters: the graphics context, the center coordinates of the spiral, the current angle value of theta, the color of the planet, and the radius in pixels. The very first step is to calculate the position of the planet along the spiral path. We call the helper method spiral point, passing the center and the angle. This gives us an exact x and y coordinate on the spiral curve. Next, we adjust the position slightly by subtracting half of the planet's radius. This ensures the circle is centered exactly at the spiral point, instead of being drawn offset to one side. After calculating the position, we prepare to draw. We set a stroke style, 3 pixels thick, with rounded caps and joins. This makes the small connecting line appear smooth and polished. We then compute a second point, slightly behind the current angle, by subtracting 0.12 radians from theta. This point is used to draw a small line segment from the back of the spiral to the current position. Visually, it gives the planet a nice motion effect, like a tiny tail or direction marker. Now we set the drawing color to the color passed into the method. First, we draw the line segment from the back point to the current planet point. Finally, we draw the actual planet itself. We use fill oval through the ellipse 2D class, passing the adjusted x and y coordinates along with the planet's diameter. This produces a solid colored circle right on the spiral path. So in summary, this method calculates where the planet should be, adjusts the position, draws a short trailing line to indicate motion, and then renders a filled circle in the chosen color. Together, these small details make the animation look lively and smooth, instead of just a dot moving around. This helper method, draw in or swirl, is used to add a decorative spiral in the center of our animation. First, we set the drawing color to a gray tone with some transparency, so it blends softly with the background. Then we define a stroke about 1.75 pixels wide with rounded caps and joins, which keeps the swirl looking smooth. We create a new Path 2D object to hold the inner spiral and use a Boolean flag called first to handle the starting point. Inside the loop, we step through angles up to 4 times pi, multiplying each by 0.55 to make the spiral tighter than the main one. For the first point, we move to its position, and for all others, we connect with line 2. Once the loop is complete, we call draw method to render the small swirl. The result is a subtle inner spiral that adds depth and makes the overall animation more visually appealing. In the paint component method, we start by calling super to clear the panel before drawing. Then we create a graphics 2D object from the graphics instance, which gives us more powerful drawing features. Right away, we enable anti-aliasing through a rendering hint. This smooths out lines, curves, and edges, so the spiral path and planets look clean and polished instead of jagged. Next, we calculate the center of the panel by taking half of its width and half of its height. These values, Cx and Psi, will act as the origin of our spiral. Then we set the stroke to our custom spiral stroke, and change the drawing color to the spiral's gray shade. With these settings, every line we draw next will appear smooth, rounded, and in the right color. Now we create a new Path 2D object, which will hold the entire spiral line as a continuous shape. We also set up a boolean called first. Here we loop through the angle values, starting from 0 and going up to theta max in small steps of 0.02. For each angle, we call the spiral point method to calculate the exact x and y location on the spiral. If it's the very first point, we use move to so the path begins at that position. For all the other points, we use line to connect smoothly from the previous point. This process builds the entire spiral curve one point at a time. Once the path is built, we call draw method to render the spiral onto the panel. After that, we draw each of the planets. The first planet uses T1 for its position, with a coral color and a radius of 21. The second planet uses T2, drawn in teal with a smaller size of 16. And the third uses T3, drawn in purple with a slightly larger size of 25. This gives each planet a unique look and motion along the spiral. Next, we call draw in or swirl, which adds a subtle decorative spiral near the center to enhance the visual effect. Finally, we call dispose method. This cleans up the graphics context and frees resources once all drawing operations are complete. This is the action performed method, which runs every time the timer ticks. First, we update each planet's angle by adding its speed. T1, T2, and T3 all move forward along the spiral. Then we set up a wrap value of 2 pi, representing a full circle. If any of the angles grow larger than the maximum spiral length plus this wrap, we subtract the wrap to bring the value back down. This prevents the numbers from growing endlessly and keeps the math stable. Finally, we call repaint, which refreshes the panel and triggers paint component, so the planets and spiral are redrawn in their new positions. And that's our spiral planets animation built completely in Java Swing. We combined math, graphics, and smooth motion to create a really unique effect. I hope you enjoyed following along and learned something new you can apply in your own projects. If you found this helpful, give the video a like, share it with other learners, and don't forget to subscribe to the channel for more creative Java tutorials. Thanks for watching, and see you in the next video.